Hello, this is Tuğba Ayhan and this video is about data converters, ADC architectures. The simplest ADC is a comparator. If the input of this comparator is above a threshold, is above a reference voltage, then the output will be logic 1, and if the input is smaller than the reference voltage, the output will be logic 0. All ADC architectures use at least one comparator of some sort. The problem with comparators, the ADCs need good resolution, so we need to convert the values of millivolts and even smaller to a logic level, which means 0 to 5 volts, for example. So we need a high gain here. High gain causes uncontrolled oscillation when the input voltage is around 0. As a solution, we put a very small hysteresis by using a very small amount of positive feedback. So we can avoid staying at this 0 point by adding that hysteresis. This is the very simple flash ADC architecture. A flash ADC architecture is also a parallel ADC, which means we have the outputs in parallel at the same time. So we have multiple of those comparators who are comparing the input voltage with a reference voltage, and the reference voltages of those comparators are different than each other. So we can get a very nice analog to digital conversion here. Here we also need a priority encoder that generates a binary number based on the highest order active input, ignoring all other active inputs. So the flash ADC is the simplest in terms of operational theory and the most efficient in terms of speed. So it is limited by only in comparator and gate propagation delays. However, they are very big. So for a 4-bit ADC, we need 16 comparators. With each additional output bit, number of required comparators will be doubled. So we need a smaller architecture. This is an example for a smaller architecture. It's called digital ramp ADC. It's also called stage step ramp or counter A to D converter. We have a free running counter here. It generates some binary values at each clock cycle. So this binary code is converted into analog again, and then it is compared with the input voltage. So depending on this comparison, the counter may go on trying new values, or it can go back to 0. If the counter value, so the value that is generated here, is larger than the input voltage, then the shift register here will also be activated. So the value, that code will be transferred to the output. The problem with this architecture is when the input voltage is high, we need to try more and more and more values. If it is low, then we can find the value with a few of iterations. So the time difference between two consecutive outputs are not equal. So we have another architecture to solve that timing problem. We are using successive approximation ADCs. A successive approximation register, SAR in short, is replaced with that counter. Now the SAR is generating the binary codes. Those binary codes are converted into analog, and depending on the comparison of that analog output with the input voltage, we can either increase or decrease the output of the SAR. So we can think this structure as an up-down counter. So when the operation is done, then we are outputting this value to the output. If the SAR is capable of outputting serial data, then this shift register can be omitted. We can as well change the counter with an up-down counter, as in the tracking ADC case. Here we don't need a shift register, because once we get the value, the first value, then the next value will either be one code smaller or one code higher than the previous one. So it has a very fast update rate. However, the binary output is never stable. Again, instead of using a counter, we can use a sawtooth signal which generates this ramp function. So it is a very small circuit compared to counter, and we don't need D to A converters. So the same problem with timing also occurs here, and we may also face with calibration drift, which is due to the values of this capacitance, resistor, and the gain of this op-amp here. A delta sigma ATC is an advanced ADC architecture. Delta represents the difference and sigma represents the summation. Here we have an integrator. Vin is integrated with the previous value of the input. Then this value is compared, so this is a 1 bit ADC, and if this value is higher than 0, then the D latch is activated. So at the output we see a logic 1. We need another op-amp structure here to convert this output value of the D latch into plus V minus V scale. So if the value at this node is smaller than V divided by 2, so if Q output is 0, then we will activate, then this output will be minus V. So this will be sum with minus V, it is inverting, and it will be compared by with 0 here. So at the end we will be looking the difference between the previous value and the current value, and then we are summing up the output to get the binary out. So as you see, an ADC, a delta sigma ADC gives 1 bit output. So if the value is around 0, then at the output we will see ones and zeros. If we have a low value but not 0, then we will have more ones than zeros. And if we have small negative analog input, then we will again have ones and zeros, but not in 1010 form. So if we want to use this structure, we also need a parallel binary number output. Then parallel binary output can be obtained from this circuitry by averaging